Okay, I'm going to do one example here for autonomous equations. And we're going to look at, oops, if I could spell, logistic growth. Okay. The idea is we want to get a model for biological systems and how things what happens in a biological system. We've seen this model, y prime equals something times y. And the idea here is we assume y is positive, and you could use this for biological growth with the idea that the number of new organisms depends on how many is there, and it's going to grow linearly. The problem is, if we look at the phase diagram for this, fixed point is going to be 0. We're going to assume that k is positive, because otherwise, if y is positive, we won't have new growth. Then if y is positive, we're going to have growth, and if y is negative, it's going to go off like that. Physically, we only care about what happens for positive, and basically this thing only grows. It grows unbounded. Right, so that is not really biologically appropriate. So that's not so good. Let's try something different. And we're going to try to build on this idea of this idea. And the idea is we're going to assume that the rate of growth depends on how many things are there. Right? So if we've got a small number of bacteria, we would expect to see smaller growth. If we have a larger number, maybe it should be growing faster. Now, before we called this some constant k, and we found out that that was not good. So we're going to call this the per capita growth rate. And instead of a constant, we're going to ask what happens if it depends on how many organisms are there. Okay? And what we want is, if y is small, that per capita growth rate should be positive. Likewise, if y is big, right, if you have too many organisms there, we would expect them to be outstripping their resources. You really can't grow, so this per capita growth rate should be negative. So the question is what's the simplest way to do that? And we're going to be focused on just positive values for y. We're not going to worry about negative bacteria. And the way we're going to do this is we're going to say there's some important limiting value at L. This is right where we start to outstrip our resources. So once we get to L, we want it to be our per capita growth rate. I got to be careful here. This is not y. This is our k. We want our per capita growth rate to be positive below that because there's more resources available given the population, and we want it to be negative here. And when it comes to modeling, we try to do is just do the simplest thing first and see how that works out. So what we're going to do is we're going to just use a linear equation. We're going to assume that when y is 0, we have some rate of growth r. And in this case, our per capita growth rate is a function of y. The slope is going to be, let's see, so it's going to be rise over run is r over L. And be careful, it's going to be minus r over L. And since it's 0 at L, it's going to look like that. Okay. And notice I can, let me just leave it at that. Okay. All right. So what do we have? we have that our per capita growth rate looks like that. And so we had y prime is k times y, so we're just going to replace that. With this thing. And now this is what we're going to call the logistic equation. Oftentimes we don't really like working with this whole thing here. So let's just call that some C. So we have that, and if I bring that minus sign in, my logistic equation looks like that. Notice this is autonomous. So I can do the phase diagram. And so I can find the stationary points. So I set the derivative equal to 0. So either this is 0 or this is 0. So L minus y is 0 or y equals 0. So this is y equals L or y equals 0. So if I look at my slope field, when y equals L, slope is going to be 0. And when y equals 0, the slope is going to be 0. If y is a little bit positive, and I'm assuming L is positive, because that's going to be the place where the bacteria or whatever organism is kind of at equilibrium here, then L minus, so if y is just a little bit above 0, L minus y is positive, so it's going to be a little bit positive. And as I get bigger, that slope is going to get bigger. It's going to max out at L over 2. Notice here as y gets bigger and gets closer to L, this gets closer to 0, and so the whole thing is going to get closer to 0. And now if I'm above L, if y is bigger than L, this is positive, this is negative. So we get something like this, and the bigger y is, the more negative my slope's going to be. So what does this mean? So that means if I start down here, it's going to slowly increase, then level out. And if I start here, it's going to decrease and level out. And if I start close to L, it's going to look something like this. So L is a stationary point, and it's stable. 0 is stationary, but notice if I get a little bit above 0, it's going to increase. So it's unstable. Okay. And I could do this in terms of the phase diagram. So for the phase diagram, we have y equals 0 and y equals L are the stationary points. And as we just discussed, if y is if y is between 0 and L, it's going to increase. If it's bigger than L, it's going to decrease. What happens for negative, just to be academic? If it's negative, then what is this? This is going to be negative. Then L minus y is going to be positive, so it's going to be negative. So it's going to look like that. So y equals 0 is unstable. Y equals L is stable. Okay. Notice this is a separable equation. So you should be able to solve this. I'm going to go through and do the solution for this, just so you can see. So I've got this differential equation. Because it's separable, I can just divide everything on both sides. And and c is a constant. Now I'm going to integrate both sides. With respect to t. And the right-hand side, this is going to be ct plus some constant k. The left-hand side is not so much fun. Notice I've got the product of two things here, so I'm going to have to use partial fractions, which is a good thing because we haven't done that in a while. So how does this go? Let's see. I've got 1 over L minus y times y. So these are first order, so I'm going to have the first thing and the second thing. I'm going to multiply everything through by the denominator. Y times L minus y. And if I do that, these things cancel. So on the left-hand side, I get 1. If I multiply this through, I'm going to get A times y times L minus y divided by L minus y plus B times y times L minus y divided by y. So the L minus y's cancel. So I get AY. Here the y's cancel, and I get L minus y. Okay. So I immediately see that, let's see, I can let y equal 0. If I do that, so this will be 0, so I'm going to get 1 equals L times B. So B is 1 over L. And then to make this 0, I can say let's let y equals L. So I'm going to get A times L, and then I'm going to get B times 0. So A is 1 over L. So plugging that back up into this integral, I'm going to have the integral of, so A is 1 over L, B is 1 over L, and then the dy dt goes for the ride, and this is c times t plus constant k. I can break this up into two integrals. This integral, and I'm treating L as a constant. And then this integral, I can pull out the constant. Okay, and now the antiderivative of this is going to be negative the log of L minus y. Antiderivative of this is plus 1 over L log of y. And again, I've got this integration constant. And what is it I'm after? I want to solve this for y. So it's going to be a mess. Let's do this. I got L's everywhere. Let's multiply everything by L. So I have minus log of L minus y plus log of y equals ct plus k times L. So let's rewrite that. So our current equation look like that. Well, I've got log of something minus log of something. This is going to be log of y divided by the other thing. So log of y divided by L minus y. I'm going to leave the right-hand side alone. To get rid of the log, I'm going to exponentiate both sides. And the e to the log gives me y over L minus y. Now here, I'm going to multiply that L through, so I'm going to have LCT plus LK. And I can write that as e to the LCT times e to the LK. And here's the thing to notice, if k is a constant, L is a constant. So e to that, that's just some constant. So I'm we have to give this a name. I've used what? I've used A, B, C, K, and L, and R. Let's just call this D, because why not? So let's see, I have y over L minus y is dE to the LCT. I'm going to multiply top and bottom by L minus y. Again, what is it I'm after is these y's. So I'm going to multiply that through. So this becomes L d e to the LCT minus y d e to the LCT. There's a y, so I'm going to move that to both sides, or move all the y's to the left. So I'm going to add this term. So y d e to the LCT equals L d e to the LCT. I can now factor out a y. Leave the right-hand side alone, and then divide by this whole mess. To get something like that. Now, if you go in and look in the book and look at the derivation of the book, you get something that looks different. It's algebraically the same. Your authors in the book kind of knew this was coming, and they did some things to make this a little nicer. And they kind of knew that this LC was going to be combined later, so they did some things to make that look a little nicer. It's going to look different in the book, but it's algebraically equivalent. Either way is fine.